In the next, we will consider a definition of the measurement of the difference between the prediction and the desired values. And therefore, we will find a way to train our neural network model. So this is the problem of defining the loss function. If you remember the element of the learning, we have the data, gives data to algorithm, and the algorithm search from the hypothesis set. In the case of neural networks, these are particular settings of the W and U matrices, and with some criteria that is the loss, so we can have some output predictor that is a deliverable of the learning process. Now in this video, we will consider the loss function. So let's delete this. To consider loss function, let us first think about the loss at one particular data point. Say, let me ignore the index of the training samples, or so on and so forth, for the clarity in the samples. Say if the desired value is y and you predict it as p. So how to measure the loss? Because y is either 0 or 1, and the p is some value between 0 and 1. So now we can discuss that according to different cases. If y belongs to 1, we can use this kind of. How about, given that the probability model is, let's say let the probability model were as predicted. So with probability p, y has the value, the class is 1, and now your observed class is y. Then how likely is this situation? How likely we have observed y is y given the probability of y equals to 1 is p. This is a little bit a mouthful, but if you consider it carefully, it makes sense. So if the observed y is 1 and the probability of y is 1 is p, so this event occurs with the chance of p. If the observed value is 0, but we have predicted that y equals 1 with probability p, then we will see the probability of y equals 0 according to the predicted probability of y equals 1 is 1 minus p. Okay, if we summarize this argument mathematically, we can use y as a switch. So now we can see, let's see, if y equals 1, we will make the y on the power of p, and this is times y minus p, y minus y. This equation summarizes all the discussion above. Now when y is 1, this becomes 0 and this part is switched off. And this equation gives us p when y is 1. When y is 0, this part is switched off. And this equation gives us y minus p. So in conclusion, this is p observed y when the class is 1 is p. Okay, this is for one value, which is a reasonable construction. How about if we have multiple samples? A very important assumption in a lot of learning problems is that independently distributed samples. That means the performance of the model is independent. Well, not the performance model. Excuse me. It is the class, the sample, the data sample are independent with each other. Therefore, the class of yi is independent of the class of yg. So, therefore, if we consider the probability of observing a series of independent events that are those are p y1, given that the class of x1 is 1, this event is of the probability of predicted class 1. And the event to observe y2, given that the class of sample 2, let's say sample rather than x1, sample 2 is 1. This event is predicted value 2. So on and so forth. We go this over all training classes, training samples. The probability of all those independent events happen together will be the product of all individual probabilities. Therefore, put it together, the probability of observing the training annotations as they are given the model prediction would be P1 Y1 1 minus P1 1 minus Y1 times P2 Y2 1 minus P2 1 minus Y2. This is the likelihood of observation. So to fit the model to the data is to let the model's prediction to be consistent with the reality, and the purpose is try to maximize this quantity. To maximize this quantity, it is analytically difficult when we are dealing with this long series of multiplication, and numerically difficult because each of those quantity is smaller than 1, if you have something like 70 such quantities multiplied together, you will have a very, very tiny value that will be exceeding, will be underflowing the minimum number that could be processed by a digital computer. So in practice, we will actually dealing with the log likelihood. If we take logarithm of this quantity, this will give us very neat equation that because you take in the logarithm, that will make the series of multiplication becomes a series of summation, and then we will have sum over all training samples pi yi I need to take the logarithm of them. So by taking the logarithm, this power becomes a multiplication yi times log pi, and this multiplication becomes a sum plus y minus yi times log y minus pi. So this will be the logarithm. Let's implement this. So the equation is now simple enough. So after this long derivation, the implementation itself is pretty straightforward. Let me remove this derivation and come to here as to depth loss function. We're given the prediction and the true value of the y. So therefore, we just need to return this. Y times numpy.log prediction plus 1 minus y times np.log 1 minus prediction. And note that both y and prediction could be vectors, and the computation will be executed element-wise, and the result is a vector, and we'll take the sum of the vector. But in practice, we often take rather than the sum, but the average. That does not change the nature of training, because whatever kind of change in the parameters will make the sum of the likelihood larger. It will correspondingly make the average larger as well, but this will make it numerically more stable, because that will make the scale of the gradient of the adjustment in each step independent with the number of training samples we want to consider in each step of the training. So there is only one inconsistency we want to address. That is the semantic of the definition. Look, this function is named loss. As we have discussed, we need a loss function in the training algorithm. But loss refers to something bad. However, this computation refers to the likelihood. The likelihood refers to something good. You want to make the likelihood as large as possible. That means, according to your model's prediction, what has been observed has a large probability of being observed. That is, your prediction is more in alignment with the reality. So this is a good thing. You want to push it up. But the name of the function refers to something that you want to make it smaller. Therefore, we simply put a negative sample here, which is a common practice in machine learning. We always want to minimize a loss function. if this is a good thing to have, we make it negative. Therefore, this is loss function, which is called negative log likelihood. You can Google this term and you will find some more discussions on the internet. So let's try this function. I think we need to define this again and print loss prediction and y train. So we have such a loss.